Salutations, mini mathematicians. I hope you're having an awesome day. You've been doing such great work working through Module 6, and we're still just going to be exploring our number system. So today what we're going to do is we're going to be classifying real numbers into the number sets that you're all so familiar with already. So our purpose is to determine all number sets of value determine all number sets of value belongs to in the real number system. So we're classifying. Awesome, let's get started. So the first thing we're going to be looking at is we're going to list the sets of numbers we've learned about so far. So maybe you remember the smallest set. Do you remember what the smallest set is called? That's right, the natural numbers. So the first set we learned about is the natural numbers. And then after the natural numbers, remember, numbers we see in nature, we can see one pumpkin, we can see two pumpkins, we can see one pig, we can see two pigs, we can see 3 sheep, we can see 8 sheep. But what we need to talk about then is we need to talk about when there isn't anything there, because you can't see something when it's not there. Are you? We should talk. We should talk. So when there's something that's not there, that's the number 0. So that's when the whole numbers come in. So the whole numbers are all the natural numbers plus 0. Remember, it looks like a hole, right? The next set of numbers after the whole numbers are the integers, and that's when we first start having the negative numbers. So that's all the whole numbers and their opposites. So again, still no fractions and no decimals, no partial numbers. That's where the rational numbers come in. And then we kind of have this other set. It's not really connected to any of these. It's when it's not any of those. And those are the irrationals. And we looked at those last lesson. And when we noticed that irrational numbers are decimals that are non-terminating and non-repeating. So here's our big question. Are all numbers rational? No, of course not. All numbers are not rational because remember, some are irrational. So no. Some numbers cannot, and let's think about the definition of a rational number. A rational number is any value that can be written as a fraction, p over q, where q is not 0, and p and q are both integers. So now some numbers cannot be written as a fraction of integers. There are irrational numbers, such as my personal favorite, pi. Also maybe 2.12335 or just keeps going, right? So these are irrational numbers. They're decimals that never terminate and never repeat. So my next question for you is, do you think the square root of 2 can be written as a fraction where the numerator and denominator are both integers? What do we think? Do you think you can do that? Some of you might be like, oh, square root of 2 over 1, it's a fraction. But it's not a fraction made up of integers because square root of 2 is not an integer. So the answer to this is sadly no. Square root of 2 is irrational. A square root of any non-perfect square is a never-ending, could say never terminating, that kind of sounds more mathy, right? Never terminating and non-repeating decimal. Hence, cannot be written as a ratio of two integers. Therefore, is not rational. So in fact, the square root of a non-perfect square or decimal amount of a non-perfect square is going to be irrational. And what I mean by that, 25, square root of 25 is 25. And if I have the square root of 2.5, so if I take a calculator and use the square root button, which is forbidden this module, unless we're making a point, right? So square rooting and squares are inverse operations. So notice here's my square button. So if I did 5 squared, it's 25. So if I press the second button and I press the x squared button, I get the radical square root symbol. If I put 25 in there, I get 5. If I put 2.5 in there, I also notice it's 581,13883. Notice that's going to be a it's not a perfect square, right? It's not rational. So remember that. So let's take a look at number 4. So irrational and rational numbers form the set of the real numbers. So we're going to create a Venn diagram to show the relation between the sets of numbers in the real number system. So this is our first part of our Venn diagram. And how a Venn diagram works is any overlapping part is what they have in common. So everything is going to overlap in the real number system because all these number sets are in the real number system. So the first thing we're going to start with, and we made a similar diagram to this in Module 1 when we first were exploring the real number system. So the first set of numbers we're going to look at is the natural numbers. And that starts with the 1, 2, 3, and then continues. And then the set of numbers that includes all the natural numbers and is still a real number is the whole numbers. Remember, that starts with 0 and then goes 1, 2, 3. So notice it includes all the natural numbers and then the whole numbers. And the next set of numbers that includes all the natural numbers and the whole numbers are you can look up above, that's right, those are the integers. So those integers, and that starts with starts with an ellipse, and then -2, -1, 0, 1, 2, 3, and another ellipse. So notice that's going to include all the natural numbers, all the whole numbers, and still be a real number. And then after the integers comes the rational numbers, ratio now. Ratio now. Helps remind me how to spell it and what it means. It means any number or any value that can be written as a fraction of integers. And notice you're like, oh my gosh, Mrs. Bartha, we can't include our irrationals over here. Well, irrationals are not part of this group. Notice these are all overlapping: naturals, whole numbers, integers, rationals. The rationals include all these. The irrationals are kind of off on their own. So they're still part of the real numbers, but they're completely separate from the rationals, integers, whole numbers, and naturals. So they're still included in the real number system. I can still place them on a number line. So the real number system is also thought of as the number line. You can put any real number on a number line. And so irrationals we can also place on a number line. For example, if I wanted to put pi on a number line, I would put it between 3 and 4, right? A little closer to 3 because it's 3.14. So irrational numbers And those are the non-repeating and non-terminating decimals. We can also remember that it's the square roots of non-perfect squares. Dun, 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 dun. Important. Okay, so now that we have this handy dandy Venn diagram, let's talk about square roots of a negative number within the real number system. So if there's a number in the real number system, we should be able to place it on a number line. But if you look at the square root of negative 49, this says there's some number times itself that equals negative 49. Well, there's no number times itself that's going to equal a negative, because a negative times a negative is always a positive, and a positive times a positive is also going to be a positive. So in fact, this is not real. This is not a real number. So the answer is, can it be simplified within the real number system? No. Cannot be placed on the number line. This number, it's not rational, it's not irrational, because it's not real. No real number times itself can equal a negative. So for you, at this time, the square root of negative 49 is imaginary. Imagination land. Imaginary. So it's not real. Things that aren't real, they're imaginary, right? When I was younger, I had, I called it my invisible dog, right? And he wasn't imaginary, because I was like, it's real. I can see it. But they were imaginary, right? My imaginary dogs. Okay, so explain the difference between negative square root 4 and square root of negative 4. Well, the negative square root of 4 equals negative 2, an integer, rational, and real. It's just the opposite of the square root of 4. You can think about that negative sign also meaning the opposite. However, if we take a look at the square root of negative 4, it's not real. We can call it imaginary, but all you have to know right now is that it's not real. It's not real. It's not irrational. It's not rational. So not rational, not irrational. No number times itself is negative. Okay, so now what you're going to do is we're going to be classifying each of these numbers by writing an X under the sets to which it belongs. As you do this, you're going to classify into all the sets it belongs, and you might want to think about simplifying them or seeing if they can be simplified. So for example, maybe you want to simplify the square root of 36 before you get started. 2/3, it's not natural because it's a fraction. It's not whole because it's a fraction. It's not an integer because it's a fraction. It is rational. Oops, they want an X. And real. It's rational and real. So go ahead and finish the rest of the problems. And number 20, you might want to draw a quick picture, and we'll go over the answers as soon as you're ready. Are you ready, kids? Okay, let's take a look. 0.25 is a terminating decimal, so that's rational and real. -2, it's a negative value, so it's a negative whole number, which means it's an integer, rational, and real. Square root of 5 is irrational. It's the square root of a non-perfect square, but it's also real. 0 is a whole number, an integer, a rational number, and real. Square root of 36 is equal to 6, which tells you it is natural, a whole number, an integer, a rational number, and real. 36 is a perfect square. -121 square rooted is undefined. It's unreal. You can think of it as undefined right now for yourself. We can also think about it as imaginary. Here, this 3 is repeating, so I know that it is rational and real. 10/13, it's written as a ratio, so that means it's rational and real. -3 square root of pi is irrational and real. If you have an irrational number like pi, if you multiply it by any integer, any rational number, it will still be irrational. It's repeating. Take 3 groups of it, it's still repeating. Sorry, it's non-repeating and non-terminating. Take 3 groups of it, it's still non-repeating and non-terminating. Taking a look at 8/0, this is undefined, so it's also unreal. It's not imaginary though, it's literally just undefined. Square root of 2/2, that's irrational and real. Square root of 2 is irrational. You take half of an irrational number, it's still irrational. Here, there's no pattern, right? It's not repeating, it's just like a pattern you see. So it's irrational and real. And the last one, if you look at a side of a square with an area of 8, you might want to think about drawing a picture here like I suggested. If the area is 8, we're talking about just the side length here though. So the side length is the square root of 8, which means it's irrational and real. The square root of any non-perfect square is irrational. Great job, mini mathematicians. I hope you did awesome classifying these numbers in the real number system, and I will see you next time. Great work. Remember to be kinder than you have to.